Okay, we're going to look very briefly at capacitors. This is the symbol for a capacitor. You'll notice it's very similar to the symbol for a cell, except that the lines are of equal length. Now, all a capacitor actually is two plates of some conducting material with some insulator in the middle, or dielectric. Now, what this means is that when it's connected to a circuit, current can flow to a capacitor, but it can't flow through it. That insulator stops electrons from flowing between the two plates. But what we can end up with when I connect it to a battery or to a cell is that electrons will flow and build up on this plate, and it will become very negatively charged and repel electrons from this plate, which will flow back to the battery, and it will become very positively charged. What this means is that if I apply some voltage across it, it will charge up until it has an equal and opposite voltage across it. Basically, you will end up with two power supplies in the circuit. You will have cells trying to push current in one direction, charging the capacitor until it is pushing those electrons back in the opposite direction. And then, of course, no more current will flow. Now, that's not entirely useful in itself, but in circuits, these capacitors can do all kinds of different jobs. We can use them as filters. We can use them to smooth circuits out and get rid of variations in current. They can also be used as very temporary power supplies. So really, really useful devices. Now, we measure capacitance in farads, and 1 farad is defined by an equation which is Q equals VC, or if you prefer, C equals Q over V. And so 1 farad capacitor is a capacitor that will store 1 coulomb of charge if it has a potential difference across it of 1 volt. So capacitance is a measure of how much charge could we store on those plates for every volt of potential difference between us. The energy stored in a capacitor can be found using this equation, half QV, which is the same as half CV squared, which is the same as half Q squared over C, and not dissimilarly to when you worked with power and electricity in Module 1, you've just got to choose which one of those equations makes most sense in any given situation. But that's how you work out the energy stored on a capacitor. It's worth just reminding ourselves that power is just the rate of energy transfer, so it's energy per used per unit time. So if you know the energy stored on a capacitor, a common question can be, if this capacitor discharged fully in this time, what would the power have been, or the mean power have been? And that would, of course, be E over T. Now, you need to be careful, because that question used the word mean when it was talking about power. What's the average power supplied if it got rid of all of that energy? Because when a capacitor charges or discharges, generally speaking, it will do so in a way where current changes. Now, it is possible to charge a capacitor with a constant current by changing a variable resistor that's attached to it. Now, that's how we derived this equation, by doing an experiment like that. But in reality, left to its own devices, capacitors will want to follow exponential patterns. That's because as you charge it, it gets harder and harder to add an extra charge, and as you discharge it, the repulsive force expelling those electrons from it gets less and less as the charge built-up reduces. So what we end up with for all of our discharging capacitors is an exponential decay equation. So if I were to draw a graph against time for a discharging capacitor, and I could make this axis V, I, or Q, any of those, I would see this exponential decay. So let's work in terms of Q. We'd call that value Q naught, the starting amount of charge stored, and then we could see how that decayed over time. Now, because this is exponential decay, it would follow an equation of this form. Q equals Q naught, the initial charge, times E to the power of minus T over RC. That's a very similar form to the decay you will see for damping. It was similar to the decay you will see for radioactivity. They always follow a very, very similar pattern. There are a few things worth drawing our attention to. That minus sign means that it's decaying. This value here is going to get lower and lower as T increases. RC is a very useful thing to consider. This must have units of seconds, because this whole exponent must have no units at all. So if this has units of seconds, this must also have units of seconds. So RC has units of seconds, and we call it the time constant of the circuit. It is the thing about this circuit that determines how fast our capacitor discharges. Now, we haven't mentioned where the R comes from yet, but in reality, if I'm going to discharge a capacitor, I will discharge it through a resistor. And that resistor will control how fast the current can flow. So it will control the speed of this decay. The bigger the resistor, the slower this will happen. Similarly, the capacitance, the amount of charge we've got stored in the first place, that will also have a significant effect. So RC is the time constant of the circuit. Now, this equation is difficult to work with as it is, and so one of the most common things you'll be asked to do with it is to rearrange it. And the easiest way to rearrange it is to use logs, especially if we can get it into a straight line format. So if I were to take logs of both sides, I'd end up with log Q equals log Q naught minus T over RC. Now that very easily could be converted into a straight line of log Q against T. You can see that my gradient would be equal to 1 over RC. My intercept would be the log of Q0. So from this graph I could work out what was the initial charge on the capacitor, and from the gradient I could work out what's the time constant of the circuit. It's probably worth adding a minus sign in there. The gradient is minus 1 over RC. So from that I could work out the value of resistance or of capacitance if I knew the other one. Now this equation and this rearrangement is exactly the same for current or for voltage.